Hi everyone, I am Mrs. Fitzpatrick, and today we're going to be talking about Taylor series. So, in this lesson, essentially what we're going to be doing is finding polynomial functions that can be used to approximate transcendental functions. Example of transcendental functions would be like your e to the x function, your natural log of x function. Okay, so let's get started. If p of x is a polynomial function, used to approximate some other function, f of x, they must contain the same point with some x value c. Okay, so that means at some point they need to have the same coordinate, right? P of c is equal to f of c for some value of c. To be a better approximation, it would be even better if at that point they had the same slope. So that would mean that the derivative p prime of c would equal f prime of c at that x value c. For even greater accuracy, you'd want the second derivative to match, right? So p double prime of c would equal f double prime of c. So you can kind of see how we're taking this new function and we're wrapping it around the original function to try to get it as close as we can. So putting this all together, it actually gives us our expansion for Taylor polynomials. And so let's go ahead and fill in this box here. So it says, if f of x has derivatives of all orders, it can be approximated by this Taylor polynomial. So it's p sub n, and this is like an nth degree Taylor polynomial of x is equal to f of c. Remember, that's that first point we're choosing to be the same as our function, plus f prime of c times x minus c, plus f double prime of c times x minus c squared over 2 factorial, plus f triple prime of c times x minus c cubed over 3 factorial. And you kind of get the point, right? It's that pattern. So we have f, the nth derivative of f of c, times x minus c to the n all over n factorial. And so this is called an nth degree Taylor polynomial. And it's centered at the c of our choice at x equals c. Okay? Now, there's a very special sub-Taylor polynomial called a Maclaurin polynomial. And essentially all that is we're choosing the c to be 0. So basically if we plug in 0 for c, for all of these terms, we end up with an nth degree Maclaurin polynomial, which would be p sub n of x, which equals f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial, right? And you get the point. Plus the nth derivative of f evaluated at 0 times x to the nth over n factorial. Okay, So in these notes, I like to make a table for these problems. So once again, they won't give you a table like this. So take note of kind of how I do this because you're going to want to know this process when it comes to finding a Maclaurin or a Taylor polynomial to approximate a function. Okay. So first example, we're going to use the definition of Maclaurin polynomial to find the fifth degree Maclaurin polynomial for f of x is equal to e to the x. So the table is going to kind of help us create a polynomial based on the form that's written above. So we need to know f of 0. We need to know f prime of 0 times x, right? F double prime of 0. And so this table is going to help us do that. Now, luckily, our function is e to the x. So f of x equals e to the x. And because it's centered, right, because it's a Maclaurin polynomial, it's centered at 0. So c is 0. And that's the number we're plugging into all these derivatives. So e to the 0 is just 1. And the great thing about e to the x is its derivative is just e to the x. So we can fill that out all the way down. It makes it really nice and easy. And which means we're plugging in 0 to e to the x for all of these. So all of these derivatives evaluated at 0 are just 1. Okay, so the fifth degree Maclaurin polynomial, we're going to use that form that's just right above it. It's f of 0, which is 1, plus f prime of 0 times x, which is just x, plus we have f double prime of 0, which is also 1, times x squared over 2 factorial, right? This should look familiar from that previous lesson that we just did. And then we have x cubed over 3 factorial. That's because our third derivative is evaluated at 0, is just 1. And we're going all the way to 5th degree. So plus we'll have x to the 4th over 4 factorial plus x to the 5th over 5 factorial. Okay, this polynomial is a good approximation for f of x equals e to the x. By extending the pattern into an infinite series, it actually becomes exactly correct instead of an approximation. And so it would be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, right? Plus, we'll go ahead and do our general term, x to the nth over n factorial plus dot, dot, dot. And then you can put that in sigma notation too, which is the sum from n equals 0 to infinity of, we could write it as x to the nth over n factorial. Note 0 factorial is 1, so this does work out to be equivalent. Okay, so let's go ahead and move on to another section. So we can extend this out just like we did in that last problem to an infinite series. So instead of just having a Taylor polynomial, you can just add a dot, dot, dot at the end in a general term, and it turns into a Taylor series. So if you have a Taylor series, it's going to be written as f of x equals f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared over 2 factorial plus f triple prime of c times x minus c cubed over 3 factorial, right? We'll go ahead and do our general term, f, the nth derivative, at c of x minus c to the nth over n factorial plus dot, 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 right? Only difference is we're not picking a finite number of terms here. We're going to go off to infinity, and it becomes exactly equivalent to your original function. Okay, Maclaurin series, we're going to center this at 0. So it would be f of x equals, instead of c, we're going to plug in 0. So f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial plus, keep going, we'll do our general term, the nth derivative evaluated at 0 times x to the n over n factorial plus ... right? So anytime you read a problem and it says Maclaurin series or Maclaurin polynomial, it's the same as a Taylor series, it's just centered at 0. Okay, so these formulas allow us to form a power series for functions that cannot be written as a geometric power series, which is what we kind of did in that last lesson. Okay, so let's take a look at an example. So it says, use the definition of a Taylor polynomial to find the fourth order Taylor polynomial and the Taylor series for f of x equals cosine of x centered at c equals pi. Okay, so f of x equals cosine of x. So we're going to fill that into the table. Remember, this table will not be given to you on problems like this. Now we're going to plug in pi. So cosine of pi is -1. Now the derivative of cosine is negative sine of x. Negative sine of pi would just be 0. And then the derivative of negative sine of x is negative cosine of x. Negative cosine of pi would be +1, -1, right? Derivative of negative cosine of x would be positive sine of x. And the evaluated at pi, sine of pi is 0. Derivative of sine of x is cosine of x. And cosine of pi is -1. Okay, so the fourth degree Taylor polynomial, that's p sub 4 of x, right? This is just going to the fourth degree. It's always your function evaluated at now pi, because that's what your c is. So -1 plus, now the next term is gone, right? Because we're multiplying it by 0. So keep that in mind. And so it would be like 0 times x minus pi, right? Which is just 0. And then it would be 1, which is just 1, right? Times x minus pi squared, right? Over 2 factorial, okay? And then the next one, now it's times 0 again. So it would have been 0 times x minus pi cubed over 3 factorial, but that's just 0. Then the next one would actually be negative. So I'm going to write it as -1 times x minus pi to the 4th over 4 factorial. So this is the fourth degree Taylor polynomial. Now, this would get you an approximation of cosine of x, but it's not exactly equal to cosine of x. So this is approximately cosine of x. Now, to get exactly equal, we have to extend this out to an infinite series. So it would be -1 plus x minus pi squared over 2 factorial minus x minus pi to the 4th over 4 factorial plus, let's do 4 terms. So the next one would be x minus pi to the 6th over 6 factorial minus ... Let's do a general term here. So I like to do the first 4 terms and a general term. And so your general term would be, now be careful, it's x minus pi to the, be careful, notice we're only looking at even powers. So we're going to do 2n over, and it's going to be 2n factorial. So you can index it starting at 0, and that should work out to get you everything. The only thing that this is missing is it also is alternating sign. So you need to incorporate that by multiplying by -1. And we can do, let's see, we're going to index this at 0. We're going to want to do n plus 1 so that it starts as a negative value and alternates from there. Okay, so we have our Taylor series. And so now it says use your Taylor polynomial from the example above to approximate cosine of 3. So we have p sub 4 of 3. We're just plugging in 3 for x, which would be -1 plus 3 minus pi squared over 2 factorial minus 3 minus pi to the 4th over 4 factorial. And when you punch that into a calculator, you get about -0.990. So cosine of 3 is approximately -0.990. Okay, which makes sense because cosine of 3 is pretty close to cosine of pi, which is -1, right? It should be a little bit, I guess, more, but less in absolute value than 1. Okay, so let's go ahead and move on to the next step. So go ahead, now's a great time to pause the video, do let problems 3 and 4 on your own, and then we can come back and do it together. Okay, so example 3 says, use the definition of a Maclaurin series to find the Maclaurin series for f of x equals sine of x. Remember, Maclaurin means it's centered at 0. This chart will not be provided for you, so you need to kind of understand how to set this up to make it really easy to find those polynomials. Okay, so f of x is sine of x. Sine of 0, okay, so sine of 0 is 0. And then we're just going to go down the line and take derivatives. So the derivative of sine of x is cosine of x. Cosine of 0 is 1. Derivative of cosine of x is negative sine of x. Negative sine of 0, still 0. We have f triple prime of x. So the derivative of negative sine of x is negative cosine of x. We end up with negative cosine of 0, which is -1. Or sorry, negative 1. Just -1. Sorry, -1. And then derivative of negative cosine of x is going to be positive sine of x. Sine of 0 is 0. And then the derivative of sine of x is cosine of x. So this at least gives us quite a few terms actually for this. The reason I went so far on this table is because a couple of the terms cancel out or zero out, right? Because of those f of 0, f double prime of 0, right? Those are gone. So you're going to want to do enough to get a good pattern for the series. Okay, so cosine of 0 is 1. Okay. So f of x equals sine of x. We're going to find the Maclaurin series. So we always start with f of 0, which is 0 in this case. So that term's gone. And then plus f prime of 0, which is just 1, times x, right? So we start with x, plus that next term zeroes out. It would be 0 x squared over 2 factorial, right? That's gone. But then it's plus a negative, so I'm going to write it as minus. And then we have 1 times x cubed over 3 factorial. Then it would be plus 0 times x to the 4th over 4 factorial. That's gone. And then plus x to the 5th over 5 factorial. It's because it's times 1. Now, because this is a series, this is going to keep going. And this is an alternating series, so it might have been a good idea to maybe go a couple more rounds to go have 4 terms. But you can see the pattern here. We're getting odd degrees. It's also alternating between 1 and -1, right? If we kept that continuation going. So if you did need to do a general term for this one, this is how I would probably write it. We could write it as x to the, now we want the odd powers only. So we could do 2n plus 1. We can index starting at 0, and then that should give us all the odd numbers. And then 2n plus 1 factorial. And then be careful because it is being alternated. So we have -1 And then I think we can go, because it starts with a positive, just to the end. Plus dot, 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 right? It would keep going. Okay, number 4. It says, find a power series for f of x centered at c equals 1 if f of 1 equals 2, and the nth derivative of 1 is n factorial. Okay, so what we want to do is we want to set up a table. And I'm going to set up this table with different values of n. Okay, so n is the derivative number, right? So n, if when n equals 1, it's the first derivative. But it actually gives us that derivative using the formula. So I'll show you in a second. So the first one would just be if n equals 0, that's the 0th derivative, which is just f of x. And so f of 1 is given to us as 2, right? Okay, so then when n equals 1, this is f prime of 1, which is n factorial. 1 factorial is just 1. So we can keep filling this in. When n equals 2, we know that f double prime of 1 equals 2 factorial, which is just 2. So that's just using this guy right here to get these values. Okay, when n equals 3, let's go ahead and do 2 more. This is the third derivative, f triple prime of 1, because that's where it's centered, right? Equals 3 factorial, which is 3 times 2 times 1, which is 6. And then n equals 4 would be the fourth derivative of 1. And that would be 4 factorial, 4 times 3 times 2 times 1, which is 24. Okay, so now we're just finding the power series. So it would be f of x equals, we always start with f of c, which in this case is f of 1, which is 2, plus f prime of 1 is just 1 in this case, times x, actually I can just write it as x minus 1 over 1 factorial, we don't need to write that, just 1, plus the next f double prime of 1 is 2 times x minus 1 squared over 2 factorial, plus we now have 6 for f triple prime times x minus 1 cubed over 3 factorial, plus 24 times x minus 1 to the 4th over 4 factorial, plus dot, dot, dot. Now, it never asked us for a general term for actually any of these problems. So if it doesn't specifically ask, you don't need to write one. I like to do it just for practice because sometimes they do ask for one. And then you could absolutely simplify this. And so we actually end up, when we clean this up, with f of x equals 2 plus x minus 1, plus the 2 over 2 is just 1, so x minus 1 squared, plus 6 divided by 3 factorial is also 1, so x minus 1 cubed plus 24 over 4 factorial also cancels out. So we have x minus 1 to the 4th plus dot, dot, dot. And actually, now that it's simplified, you would think it would be easier to come up with a general term, but it's pretty hard because your first term is 2. So you could easily do 2 plus and then write the rest of the sequence. But in this case, it's a little bit tough to write those next ones. Okay, so that is it for this lesson, and thank you so much.